Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 3.51. The problem statement says, a thermostat control with dial markings from 0 to 100 is used to regulate the temperature of an oil bath. A calibration plot on logarithmic coordinates of the temperature, T in degrees Fahrenheit, versus the dial setting, R, is a straight line that passes through the points R1 20, T1 110, and R2 40, T2 250. Part A. Derive an equation for T Fahrenheit in terms of R. Okay, well, they told us in the problem statement that a log plot gives a straight line. So there's a log exponential relationship between R and T. Okay, so I wrote that relationship down right here. So now we just have to model this. They gave us 2 points here and here, and so we just have to model what these points will do on this kind of relationship, and so we've turned it into a straight line kind of looking thing. So 2 points, use this straight line linear model, and we can solve for the slope and intercept of those points. Okay, so this is a system of 2 equations, 2 unknowns. I broke down the linear algebra method here in case you were interested of how to do that. So you solve the matrix equation by doing this. I left one step out here. So x equals the inverse of A times B. So if you know how to do matrix math, you can solve for x by using this method. And so I solve for our slope and our intercept here, and then I converted it back into alpha and beta so that we could put it into this form, right? Okay. And then they told us to show what t equals, and I said t equals in terms of our this equation, or you could also use this equation. Then they said for part B, what does R equal when T equals 320? And I got 49.3. So just using our equation here. All right, so for part C, it says, suppose you set the thermostat to the value of R calculated in part B, and the reading of the thermocouple mounted in the bath equilibrates at 295 Fahrenheit instead of 320 degrees Fahrenheit. Suggest several possible explanations. Okay. One possible explanation is that we only used 2 data points to make our model. So maybe this relationship is not actually that good. Maybe we need more data that go across the whole data set so that we can get a better fit to the data. The other thing that we need to watch out for is that our 2 data points were in the temperature range of 110 and 250, and so we're extrapolating when we put in 320. So that is out of range for where our data was collected. So we're bound to have some large errors if we're extrapolating that far away from our data set on which we built the model. Another thing that I thought of is, okay, maybe the oil is having a phase change at that 295, and so the oil is boiling. They don't say that, but maybe the oil's boiling at 295, and so it's not going to change temperature to get hotter until all of that oil is boiled off. So, and then the third thing I thought of is, okay, maybe your thermocouple is just wrong. So you insert a thermocouple, but you don't have your thermocouple calibrated correctly, and so it's giving you the wrong value. All of those things are possible. So you just have to think through each one of those things and then find out different ways to check each one of those things that don't affect the other thing. Or you could change all of the little things and check all of these things to make sure that your next experiment accounts for each one of these variables. Yeah, anyway, well, that is it for problem number 3.51. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.